All right, so let me know if you're not able to see anything on the screen. All right, you're having a simple beam system where on the screen you will see that we are looking at distributed load in this example. So you are given the general axis, you have y and x-axis with the length of L. Just a reminder, for using the appendix D, the length of your beam must L. It must be in the form of L. So for the cantilever beam, in this case, that what you see is having a distributed load and is uniform loading. Solve for the right end, which is here, the displacement over here, and the rotation over here, and then the nodal forces that you have in this beam. Assume the beam is having a constant EI, the elasticity constant value, and the second moment of area throughout the structure over here. So how do we solve this kind of simple question? First you draw the diagram. Yeah, you draw the diagram, the wall and a beam with the L and distributed load with the axis X and Y. Then you start to write the equation, right? So this is just a support diagram, yeah. What you transfer the beam structure just now, the beam structure you replace with the moment and the local forces at both ends. All this number you can refer to appendix D, yeah? All this number, negative WL squared divided by 12. On left hand side, there's a negative there, and there's a positive sign on the right hand side there. Yeah. So this one you refer to appendix D, yeah, which is here. So you refer to case number 4. You have your F1y, moment 1, F2y, your M2. Yeah. You copy all this number, convert into the diagram that you see on the top of the page there, right? You convert all this number, you just substitute all this number into all these force, then you will have what you see on the screen. This one. Yeah. Just be careful on the direction. Yeah. Be careful on the direction. So you put anti-clockwise, and this one clockwise. This one is also anti-clockwise. This one clockwise, right? All right. So then all the numbers you have there, yeah. So try to understand how you convert the one on the left to the one on the right here, right? So the one on the right here, you refer to appendix D, and then you just, yeah, substitute all the numbers there. All right. Any question for these steps? The conversion of all the numbers that you see on the screen here. Any question you want to ask me? No, eh? All right. We'll move on. So we all agree that we can convert the system into a free body diagram or work equivalent diagram that you see on the screen here. After you do the individual beam diagram, you add in the support reaction force inside the diagram here, where I draw in the red color arrow. Right? First, you draw the beam system first. You refer to appendix D. You convert the system into a diagram. That's what you see on the screen here. After that, you look at the system. You see any support there. In this case, we have a wall support on the left. You add in the reaction force for the wall. In this case, I add in 2 arrows in red color. I label as F1X and F1Y. Okay. Yeah. Go ahead. Any question?
Yes. Okay. I just remembered something.
Yeah.
I think from stress one, just
Mm-hmm.
one.
Yeah.
So would it similar similar problems where we were converting distributed loads into point loads. And I remember there was a time we, something like this particular one, let's say with pins on pin supports on both sides with the uniformly distributed load, we have only one point load, let's say in the midsection.
All right. So if you have a pin loading, the first cases, like the question you asked is that when you convert your distributed load, you have to refer to this table. Of course, you can derive with the equation that we cover. So you have different cases of different distributed load here. You have case number 4, 5, 6, 7, 8 cases. Yeah. So when you after you did this one, then you look at the support that you have. You can have pin, you can roller, and so on. Yeah, it was still back to your static or dynamic cases, but maybe when you did static and dynamic, we didn't go very deep to appendix number D, right? Yeah, so yeah, you can still use back the concept that what you learned in static or dynamics. But when you learn static or dynamic module, you only focus on very individual point, right? So in this one, we look at more than 4 degrees of freedom here. Okay, right. So then we back to this question. You add in the 2 arrow, which is a reaction force for the wall, and we know that when you have something that add into the wall, you have a moment reaction when you have something fixed to the wall. So you add in the 3 additional support there, right? So the 2 arrow and then the moment M1. Okay. So in this case, we will not for beam we will not consider the x direction because x direction do not create any moment any moment to the structure. Yeah, because the F times D, the D is 0. Yeah, this component do not create anything to the structure. It's just an axial force. So F1y, this one will create moment when you stand at point number 2. And there is a moment capital M1 here that contribute to the reaction for this beam. Okay, all right. Okay, now for chapter 4, we will not consider F1x. And just back to the question asked by Katana or Hassan just now. When you did static or dynamic, you were going to calculate what is F1x. But in this case, we don't need to consider F1x. Yeah. So you write the equation F equal to KD, and in this case, we are looking at, if you write F0 means we look at nodal displacement for the beam. So you'll have something like what you see on the screen here. So the first one, let me do some, oops, sorry. What happened to my, all right, so the first one here, the first 2 is referred to point 1. So what you have is just transfer what you have from the free body diagram that you just draw just now. Again, we are ignoring, we do not consider F1x here. Yeah. So F1y, positive, and you have a negative WL2 in point 1. So you just copy what you have from the diagram here for the first point for the F component. F1y, negative WL divided by 2. And then you look at the moment. Moment, if you the beam alone, you will have a negative WL squared divided by 12 plus the additional support that you have from the wall, you have the M1. So M1 positive, negative WL squared divided by 12. You solve for the first point already. You continue with point number 2. Point number 2, you have negative WL divided by 2 for the force component. And the moment is WL squared divided by 12. All right. Any question for the force component? F0 matrix. Any question? Anything that you're not sure or you do not know how to transfer the information from diagram into matrix form? No, Then we continue with the matrix, the K matrix. K matrix is fixed already for beam. So you just copy what you learned in the previous section. The K equal to EI divided by L cube, and all the constant value that you have, 12, 6L, 12, 6L, and so on. This side is a symmetry, which is you mirror all the number here to another side. Yeah. So, and the displacement that you have inside the system. So V1 rotation 1, V2 rotation 2. All right. The fifth next slides is just the normal mathematics solving steps. Important that you understand what you see on the screen now. All right. The next one will be we are solving this equation. After you have the matrix already, you apply the boundary condition that you have. So what are the boundary conditions we have in this case? If you have a wall, then you don't have rotation at point 1. At the wall there, you don't have point 1 not able to move. So your displacement in point 1 will be 0. Then you take this boundary condition, put inside the matrix form or matrix equation here. You can cancel or not, you can, I will not use the word cancel. You can close the respective row and column. Yeah, this is help you to solve the question a bit faster. You close for the rotation and also the vertical displacement, row and column. So at the end, you only have 2 equations to solve. The first equation, negative WL2 equal to EI divided by cube times the 12 V2 negative 6L rotation 2. The second equation, you did the same. So you only have 2 equations. Right? Any of you don't understand when I say you only have 2 equations to solve? You're not able to see it. Okay? Stop me now and ask me a question. All right. Very good. So you only have 2 equations over here from this matrix form. When you close all the respective row and column, you arrive at this very simple 2 times 2 matrix. Then you're able to solve for the question. You solve, you do the inverse matrix again, yeah, or you can use a normal simultaneous equation, yeah. So for your coming exam, you are allowed to use either inverse matrix or you can use a normal simultaneous equation. So simultaneous equation, it will take you some time to solve, but if that is the way that comfortable for you, then you can use it. Yeah. All right. In this case, I will just show you how to do the inverse matrix. Yeah. So you are solving this question. So if you if you solve, you use a inverse matrix, this one, EI divided L cube. This matrix, you move to the left. After you solve for inverse matrix, you will get L divided by 6EI, 2L squared, 3L, 6 times the term you have in the force component. Then you only have 2 equations there. You solve for displacement 2 and displacement rotation 2. All right. So you have these two. So this process from the left to right, again, you can use simultaneous equation or you can use inverse matrix to solve. All right. So again, for this module, you should always understand when you get a positive sign, what does it mean? Negative sign, what does it mean? So if you get answer like what you seen, what you see on the screen here, you get a negative WL power 4 divided by 8EI. For your vertical displacement and point number 2, you get a negative sign, means the displacement is going down, which is very logic if you look at this scenario. If in an exam, you look at the diagram, the force is pointing down, but you get a positive sign for your V2, means something wrong in your calculation. You need to check your calculation, yeah? So if you look at this force is pointing down, you should get a negative sign. Rotation at 2 is negative, so it also means that you have a clockwise rotation angle, right? Or rotation angle, right? So rotation 2, just for a reminder, the unit for rotation angle here will be radian, yeah? Will be radian, not degree, yeah? Will be radian. Then after that, you have the vertical displacement and the angle at point 2, you can solve for the reaction already. So you can solve for individual, for not individual, this one is a global nodal force. So you write back the F equal to KD equation, F1y, capital M, capital F on the left hand side, equal to cinemetrics and the displacement, F equal to KD. And recall the previous answer you get from the previous equation. You substitute inside there, and then you solve for the remaining unknown there. Yeah, the rest on the screen is just mathematical steps. Yeah, you place and then you solve. So you have 4 equations there. You solve for the remaining one. Yeah. So you have yeah, all these terms. Yeah. The rest is these mathematical steps. Yeah. So you go and solve it, you'll get something like this on the screen. So you get the original for beam analysis, you have capital F equal to KD minus F0. So on the left will be concentrated nodal force equal to KD minus your equivalent nodal force. So you just put back what you have over there. Yeah. So you have your F0, which is on this side. And just now, when you solve your previous equation, you will get your F1y equal to this one, M1 equal to this one, F2y equal to this one, M capital M2 equal to this one. So you will have this component, you only have one unknown left for this matrix. All right, so F1y, you take this one minus this one. All right, so what you solved just now, minus, yeah. So they be careful that you have a minus sign over there. You have a minus sign. So later when you do the mathematics, remember to change the notation, mathematic notation, yeah, negative to positive. Then you will get this answer. So F1y will equal to WL. Moment 1 will be WL squared divided by 2. F2y 0, moment 2 0. Yeah. So you transfer the answer into free body diagram in the global scale. So you draw this diagram is a global scale. You draw back the beam with the distributed load W. and then you put inside the reaction force on point 1 here. So from the answer, F1y is positive WL, so positive is going up. So you draw a vertical y direction force, F1y equal to WL. And then M1y equal to WL squared divided by 2, positive also. So it is positive is an anti-clockwise direction. So you just put in what you find there and then you substitute inside there. All right. So you can check. After that, you can check whether your answer is correct or not by using static equilibrium equation. All the force in y equal to 0. So you take F1y minus WL equals 0. Yeah. Moment 1 will be balanced by this equation. So this is what you learn in your static dynamics. You always have equilibrium equation and then you find the missing one. Okay. All right. So let me stop the recording at this point.